Okay. Thank you once again for coming. So I will start by calling something. Actually, we have something left from this discussion. So our previous discussion, we call it something about duality, which I'm going to use duality and addition to this lecture. So I will show you what this was this kind of function we know with space. Fenchel conjugate is this is called the Fenchel conjugate, which is defined in the dual space given by this Fenchel conjugate is given by f star of all the linear functional possible table of the x star x value of x star of x minus f of x. This is given on the whole space. This is a Fenchel conjugate, the Fenchel transformation. Sometimes we call it Lagrange Fenchel conjugate transformation. So what is it by the Fenchel biconjugate is the restriction of the Fenchel conjugate with f star on x given by so this the supplement x star and x star is the dual expression of x. This will have discussion. So this is a restriction on x. So as the last property, we stated the following theorem. If we want to divide it. So actually, it's very important. So if f is proper, well, it should be. If you want to define this, this should be proper function. F is proper and convex. Convex, what we have is this. The semi-differential of x is an element, x star is an element of semi-differential of x. This implies that x star is an element of the semi-differential of f star of x star. Provided that here, what we need is if x is reflexive, x is reflexive. If x is reflexive over space, this is satisfied.
The differential of f star at x, not on f star. X.
This is x. Thank you. This is x. If and only if it's stated here, okay, if and only if x is an element of the reflection this. If here x is reflexive, and f is again long semicontinuous. F should be long semicontinuous to all this if and only if. So just to prove this, we something here. Here. So x star is an element of semi-differential of f at x, naming that from one of them. Theorem we stated previously. This means that supremum is a tenth of this value. The supremum is a tenth here at this point x. For one of our theorem, we have this. Let y star be an element of x star. Then by the definition, f star of y star is the supremum y star y x and y is have x minus y, where y runs to this. But this is greater than or equals to for this value x, this point x. So if we rearrange this, this is y, y star. So if we rearrange this y star x minus here is equal the negative of this one. The negative of this one, adding both sides, we have this f star of star is f star star for all y star element of x star. This is to mean that this is for all y an element of x star. This is the definition of subdifferential. This means x star is an element of subdifferential f. Sorry, x is subdifferential of the definition. So the reverse is very simple. If f is reflexive, meaning that if f is reflexive, meaning that if f is lower semicontinuity, meaning that f is equal to f double star, right? So assuming that x is an element of the subdifferential, this one, x is an element of the subdifferential, meaning that by one of our theorem, f double star of x is an element of the subdifferential equation. X star if and only if it is satisfied. That's what I'm repeatedly using here. So this is equals to x star, right? X minus f star of x star. But f is equals to f double star, meaning that this f is equals to f double star. This is equals to f of x divided by one of our theorem. This is equivalent to say that x star is an element of subdifferential f of x. Subdifferential of f at x. So this, all this, if this condition is satisfied, this one direction only hold this if x only if x is only reflexive, if x is only reflexive. Now having this in mind, we can go to duality and optimization. My today's discussion will be so the Fenchel conjugate will be used as optimization method here to collect two optimizations. So my consideration here is consider optimization the infimum of f of x plus t of ax, when this is in x, where f is from x to r. This is open and static. This is from y. This one, these two functions are open, convex, and lower semi-continuous functions. And let's have an operator from x, y, which is continuous linear operator. D is bounded linear. For x and y to be normal space. So several problems are stated like this. Several application problems have kind of this form. And this kind of optimization problem, this kind of problem studied many times. And this is a very famous problem in optimization. And many application problems are studied in this form. So we are going to have two problems. This is our primal problem. This is the primal problem. And we are going to develop this dual problem so that we'll see when will be these two solutions have the same optimal value. So since f g is what? G is lower semicontinuous. Again, open convex and lower semicontinuous. G is equals to G double star. We have this. G is equals to G double star. So what will be this? The infimum of f of x plus g of x times x is equals to the infimum of f star f of x plus, I can make this to be p of x, where x is in x. So if I use the definition of G star, this is the infimum of f of x plus the supremum of y star, because ax we are in y space, ax minus f star of y star. G star of y star where this supremum is running over the dual space of Y. So this is equals to infimum and supremum Y star, and then make it like this. Okay, the supremum, the Y star, where Y star is in one space of X, f of X plus, since A is boundary linear operator, its adjoint existence is equal to this one, minus this star. We have this. Now we can interchange. If we interchange, it gives equality with this one, the supremum and the Y star, infimum over X of f of X plus S star of Y star X minus B star of Y star. So we can have here. So this is only two terms which are dependent on X, right? So I can have this, the supremum of R and the supremum of, I can take negative here, okay? Negative of the supremum of X of this, take in here Y star X minus f of X, and here we have Y star of Y star. So this is f star of minus a of X. And this is equal to the supremum of this is minus f star of minus a Y star. This is by definition, it is this one. Minus star of Y star, Y, where Y. So this problem is called the dual problem. This problem is called the dual problem. It's the dual problem. So if let alpha be the optimal value of the primal problem, and let's small s b be the solution of the primal problem, solution set. This means that the solution of the set of the primal problem is the argument of this one, or this one is this. It's the argument of the supremum of this one. Actually, this letter will come to this one. So the equality of the primal and the dual problem depends on here how we can fix them. This if sub and sub inf equal. This is kind of a minimax problem. It's kind of minimax problem. So it's just finding the saddle if we can get the saddle point of this one, or if we can have certain conditions so that the minimax problem is equal in the primal, in the dual problem of the same optimal solution. Let this be the optimal value of the dual problem. This is the dual. C is the solution of the dual problem. Solution set of the dual problem. So what is true is that it is always true that under this condition, the primal problem is greater than or equal to the dual problem. Solution of the primal, the optimal value. That this means that the optimal value of the primal minus the optimal value of the dual is greater than or equal to 0. So the optimal value of the primal is greater than or equal to the optimal value of the dual problem. This is always true, which we call it weak duality. Weak duality always holds. Generally, we have alpha t is greater than or equal to alpha d, which we call it weak duality. But the question is under what condition the duality gap is 0. Alpha t minus alpha d is called duality gap. Alpha t is different. It is alpha t minus alpha d is greater than 0. This is greater than 0. This is weak duality. So our question is under what condition? Under what condition? The duality gap is 0. So how we can make that the optimal solution of the primal problem and the optimal solution of the dual problem, their difference is 0, meaning that they are equal. So we have one error. If this holds, if the code of domain of G minus A of domain of F, if 0 is an element of this set, then we have strong duality. Meaning that alpha t minus alpha d is 0. Alpha d and alpha p is 0. So we have, under this condition, we can have strong duality. For example,
What is the core set?
core of a set is form of set A is the set of all the set of X in C, so that the cone of C minus X is the whole space. The set of X in C is the definition, the cone of set C. The cone of set C is the set of X in C. This cone of this gives us whole space. The cone of P is R plus of C. Plus C is the set of lambda is lambda is greater than this.
This is the subset of C. Or of C is the set of points in C such
The set, yeah, the cone of C is the set.
Such that the cone of C minus X is
C minus X. By the definition of this,
cone of set.
the cone of the set minus this one.
Now I have to know what's the difference. The cone of the set. The cone of a set.
Cone of set C.
It's just the positive multiples of the
positive multiples should give us sources. If I like this, oh, this assuming that this zero is an element of this set on the set, then this value. So one example of this is be so that it can be studied like this.
Can I ask a question? So the only way that zero is in the cone of somebody, zero is in the cone of C, if and only if zero belongs to C. Is that correct?
This is minus.
No. In the yeah, when is zero in the cone?
Yeah, zero is in cone. Yeah.
If zero is in C, then zero is in the cone of C.
Yeah.
Right. And if zero is not in C, then zero will not be in the cone of C.
In the cone of C.
Okay, so then for the cone of C minus X to be equal to X, zero will have to belong to the cone of C minus X.
Yeah.
So then C minus X, so zero is there.
You should take it like
it's not. Okay. Now you want X, you want zero to belong to the core of
the core of this.
So zero is there. So then the cone of this set minus zero is the whole space. So
it means that it is the cone of C on this.
Cone of C is
the whole space.
Okay. Cone of C is the whole space. Essentially, what we want is that this set has this kind of a neighborhood of Z, right?
It should be.
Okay.
It means that the cone of C is one space. Here was this. Now, we can study this and this one. It's usual primal. So this problem can be studied in the form of primal problem. This is a very common kind of problem, studying this as a primal problem. So the following will give us equivalent statements so that the duality holds, the strong duality holds. X bar B an element of X and Y star B an element of There is the following are equivalent. One, X bar is an element of the solution of the primal problem. Y star bar is an element of solution of the dual problem. And the optimal solution to the primal problem is the optimal solution to the dual problem are equal. We have zero duality. And if this happens, this will happen again. And G star of Y star equals to Y star X bar minus G of this is actually from our definition of Fenchel conjugate. This means that another equivalent statement maybe I can write this. If it happens like this, because something this also happens with a strong right. This. Thank you so much. Yes. If this also holds, strong duality holds. Actually, from this, we can say that minus A star Y star by Fenchel conjugate is a differential of F. If this happens, and Y star bar is an element of the sub-differential of G of X. Basically, we need this. This is very important. If this is an element of this one, this is an element of this one, then the strong duality holds. The strong duality holds. So my next discussion will be the extended version of studying duality with equality and inequality constraint optimization. Actually, this means that if this holds for the function which I defined earlier, right? I remember there was one point so I cannot remember the function. If we make it that function to be x of y side, it's a function of kind of this. So we can here this point decided for that function L. Now let's see the extended version of this one, which is very famous and standard form of optimization. The infimum of f of x big to gi of x is less than or equal to 0 or 1 m hj of x is equal to 0 or all j1 to m, where f g1 up to gn are defined are proper, convex, and lower semi-continuous functions. Proper, convex, lower semi-continuous functions. And hi is a real valued function, is continuous affine function. X is a normal space. So what is continuous affine function? Continuous affine function is function from a normal space to R is affine. It is affine if there exists a linear operator. We need only a linear operator. Next R. This is affine if there exists a linear operator x from x to R. Say that f of x is given by a, if there exists this one and a point and be an element of R. There exists a linear operator and a point P in R. For the company can be written this way. You can write it this way because we have to be a file function. File function. Continuous meaning that if it's bounded. If it happens that it's bounded, it's continuous affine function. Oh, so having this, so this optimization problem is simply this is just to compress it. Let x be an element x says that vi of x is less than or equal to 0 for all I, and Hj of x is equals to 0 for all j. Yes, is this. So the problem, the inequality constraint optimization problem is infimum of f over this set C. So let me have these notations. With alpha the solution, optimal solution. One. Okay, that's it, okay? And this is the solution set. Where C is what we defined there. Where C is what we defined there. So under its own or its own right, so any condition, without any condition, the following always holds. There exists one, n, which are negative, and mu one up to mu n, an element of R, not only 0. Such that let me have one counternote. Is that lambda naught the optimal value of the equality constraint optimization problem is less than or equals to lambda naught of f of x plus some I run for 1 up to n of lambda gi x plus some t runs for 1 up to n mu I each item. Under it's all right without any condition. This always holds. This is, but what is important, what is very important in optimization study is can this lambda not G1 is a question. So we don't have a grant for that this lambda naught is 1. So the very important reason follows after the following qualification, constraint qualification. Under the following qualification condition, we call it Slater's condition. Slater's condition. There exists Slater's condition says that there exists x naught, an element of the domain of f, such that gi of x is strictly less than 0. All I and hj of x naught. Hj of x naught is equal to 0 with all j. So after this condition, we have a very important result, so that it is a very important version of this one, which makes it gives us a guarantee of lambda n and type of these values, so that this holds for lambda 1 is equal to, for lambda 1 is equal to.
The first part of the theorem, is that for all x and x, all x and c?
No, for all x, because the constraint values the constraint should be here.
So we somehow extend this.
Yeah, it's this whole space X, because this the constraint functions are plugged here with a conjugate function. There is no way so that we can restricting ourselves. C by itself is this. So GIs are here, GIs and HIs here.
So should I think of these lambdas and mu's as like the branch multiplier?
But there's that Lagrange multipliers. Like it all come to define this Lagrange function, so that we discuss its results. So this I usually call Lagrange multipliers. Lambda is a Lagrange multiplier. GI, UI is a Lagrange multiplier. HI. But better if we discuss it. And with these all properties will tell us that the next discussions will tell us that there is something to do with the solution of the constraint optimization problem if we consider this solution. So considering this and manipulating with this function, meaning that we have some kind of connection with the solution of the inequality. All these properties will tell us this. So the very important reason is this term, which guarantees that lambda naught can be 1. There exists this assumed should exist under this system. Till latter condition holds. There exists this non-negative and given variables such that optimal value of the primal is original is less than or equals to n x plus j transform n this latter solution will tell us this. And as supporting information, so that about the special property of this function, I'll try to state two following results. Very positive thing about this function in this way. if X bar is an element of the solution set of the primal, there exists and flatter condition holds. Lattice condition. Then there exists lambda 1, lambda n, which are negative, and mu1, mu n, real numbers such that the following two conditions hold. One is lambda I if gi of x is equals to 0 for all second is 0 is an element of the subdifferential of f plus the sum I runs from 1 up to n of lambda I gi at x bar plus the summation j runs 1 up to n mu I of the Getachew derivative. The Getachew derivative, actually, what the Getachew derivative is known by, which is actually known in finite dimensional space. I cannot, since I have an index here, it's not easy for me to the Getachew derivative at x bar. The Getachew derivative hi at x bar. But usually, this is often but this is mostly known in finite dimensional space. In finite dimensional space. But we can use it also in infinity once we agree. Okay. So better I use this one because I have an index here. So if this is a solution in Slater condition holds, without just looking at this function, we can say that there is something with these combinations of functions, these combinations of functions. How about the converse of this? But it's not how big the converse. The converse equivalent form of its converse is this. X bar is an element of C. And there exists this. We don't need Slater's condition here. If X bar is an element of C, then there exists it. And mu1 is R such that these two conditions hold. Condition 1 and condition 2. And I g I x bar is equal to 0. 4 I 2 0 is an element of the self-differential of the plus the self of I x bar plus the solution j runs from 1 to n of mu j x derivative. This is a Getachew derivative. If this holds, then x bar is an element of the solution of the primal problem. The solution of the primal. So these are very beautiful results. That's why we need to concentrate with a function called Lagrangian function. So let's concentrate on this. Can it be negative infinite? Positive infinite? Under this might be, anyways. But if it's not, it's okay. Not care about this. The Lagrangian function is given by this. Del of x lambda mu is f of x this is lambda 1, one element of this set. Okay. So here lambdas are called the Lagrange multipliers of HI. This and there is a Lagrange multiplier of HJ. Is a supermode. It is true that if x's are in C, if this value for the functional value for the value of hi of x less than or equals to 0, and hj is equals to 0, right? Since considering these two sets, meaning that if it is in C, if the value is f of x. If it is not in C, in any case, supremum will be this is at least one condition of the positive condition. So this implies that this is f of x plus plus 0 for f of x plus infinity. Make it like this. F of x plus infinity. I can make it like this. And it's this. So this implies that if I make infinity, obviously, the problem, the original problem,
You don't have to take the infimum over a C. You can take the
is
infimum
all
over
X. All is X. All X. This is the primal originally, the original original equality equality. So this original equality inequality problem is stated as minimax of Lagrangian function. Minimax of Lagrangian function. So if we interchanging the supremum and the infimum, we'll get the so-called the dual problem of Lagrange multipliers. The dual problem of Lagrange multipliers. The primal problem is the problem of variable x. Okay, it's the problem of variable x. So, but if we interchange, the problem would be the problem of Lagrange multipliers. Problem of Lagrange multipliers. Interchanging infinite of then so-called the dual problem of Lagrange multipliers. If we interchange, we have the supremum of n negative mu and Rn if you this is called the one group. So it is true that the changing. This is really quite if those are simple linked variables. So meaning that the primal problem is greater than cos to one. The primal problem is equal to greater than cos to one problem. Actually, meetings. What? So it's just studying the minimax problem. Very good problem of minimax problem. So just to relate it with the minimax problem, maybe I can define this. The point x naught, lambda naught, y naught, and then x cross r n plus m is called starting point of if the following is not now not lambda mu L of x and mu for this case. For only. If a point is a saddle point of this one, if a point, this one is a saddle point of L, satisfy this one, then it is a solution. X0 is a solution point of this minimax problem. The supremum is the first, second in the infimum. X0 satisfy this one. This is function of X optimization of variable X, optimization of variable lambda and mu. Okay. Otherwise, minimax problem has some very huge concept because I'll use saddle point. That's why I would like to state it here. The minimax problem has many applications. Now, so the optimal solution, that means that I stated the primal of this, the optimal value. What? Alpha, the optimal solution of the primal. And S is argument of the supreme. Why I state it this way instead of saying S is the solution set of the primal? This means okay, this is a solution set of the primal. I can state it this way, but it's also important to understand it this way. This is argmax of x in x of solution set of y. Better to understand it this way. this expression to view it. We have if, so if. So if we have this, it is, as I discussed there also, we have the weak duality. That is because alpha P alpha is greater than or equals to alpha bar. So under what condition the strong duality holds again? How 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 the dual, the optimal solution of the dual is the optimal solution of the primal. The optimal value of the primal and the optimal value of the dual are equal is a question. This always holds. This always holds. So why we say that this is dual problem? Is later on I would try to give kind of examples so that this can be studied as it has a relation with the Fenchel conjugate. There's a Fenchel conjugate. So if I put here, I can have F. I can have expression of F star here. I will finally give examples so that this quality holds. This quality holds. Now let me come to the last term. I think to be the last term. Doesn't matter. I can combine all. Then the following are equivalent. One, X bar is an element of S. Okay, that's why I wrote it this way. This is the minimum, it's mean in R in last view in Rm. Okay. Alpha is an element of the solution. X bar is an element of the solution. Lambda bar, mu bar is an element of the dual solution. And the solution of the primal problem is equal to the solution of the dual problem, zero duality. Up, zero duality up. Second is if it is a solution, if X naught, Y naught, Z naught is a solution of the minimax problem, then it is a saddle. If they are connected by if and only if. X bar, lambda bar, mu bar is saddle point. And the third one is, which really shows that the previous terms which are stated are very important for someone to have this result. Someone to have this result. Second one is C. Derivatives and first condition is these three are equivalent. So if we can show that this condition also, and actually we showed, we have tried to state in the previous term that X is in C, and if you can find lambda i's and mu i's, so that this is satisfied, then it holds. It holds. But how about this? How about this in the view of Slater condition? If the solution of the primal problem is an entity, Slater condition holds. Then the solution of the primal problem is an entity, and the optimal value of the primal and the optimal value of the dual are equal. That is zero duality gamma. Zero duality gamma. So Slater condition, Slater's condition, and was good. So that I want strong duality holds. Strong duality holds. Strong duality holds. So let me have one simple example, maybe two examples. Two examples. Maybe how why is this dual? Why give it dual? Because the as you see, HI is fine function. Fine function. And we can manipulate this as the supremum of function of x and function of x stars. Can manipulate that. For example, is maybe I can study this like this. But I can have also another constraint. No problem. AI of x is less than or equals to pi. Pj of x is equals to cj. These are linear. These are linear. Very easy. Once. Let's see the duality function. Duality function. If you the Lagrangian is this. What is our GI? This one. These are all equals. This one. So the duality function. The duality function is this one. If you move off the Lagrangian, right? Can we write this? If these are assuming that this was a boundary linear groups. Meaning that this can be written as very just one. This can be taken as boundary linear. So this is this minus this Fenchel conjugate of operator H, where H is this operator, where H is this operator. So the duality function, if we manipulate the duality function, is because we have the child's continuous linear function. It involves linear operator, linear function. It's linear function, so you can manipulate it in terms of this one. So inverse, the supremum of this minus this one is just the new supremum of this, and it's this one. This is this is one example so that the primal and the dual are equal. In R, we are discussing in R. So the Lagrange function is right. This is equals to x cubed minus 1 less than or equals to the negative is this one, right? Lagrange is this. Lagrange function is this. It is true that what is solution at 0, right? At 0. At 0, and its optimal value is -1. So the primal problem is attained at x is equals to 0, and its optimal value is -1. What about the dual? So what is the infimum of lambda where x in R or x space x is R? What will be this? What is the infimum? The infimum of this one is -1 if lambda is equals to 1. True. And negative infinite otherwise. So what is the supremum over lambda and element of R plus, right? Say that stretches R plus. R plus is that this is equal to infimum. So the optimal solution, primal and the optimal solution of the dual are equal in this case. This is one of them. But this holds. I think it's good if I stop here, because my next discussion will be on the Hilbert space, proximal and numerical metrics. Thank you so much.
Very nice. But has any questions?